Hello everyone, I'm Carlotta Giulieri, PhD student of University of Perugia. My presentation title is Formulation, Characterization and Optimization of Dry Powders for Inhalation using combined micronized Levo-Dropropizine and Curcumin. The present work was done in collaboration with Aptut and Evotec Company. Here we have the agenda of the presentation, which includes scope and introduction, methods, results and discussion, and then conclusion. Aim of the current work was to optimize process and composition of previously studied dry powder for inhalation using antitussive levo-dropropizine as active pharmaceutical ingredient, combined also with curcumin. The previous work, based on the design of experiment, was performed to select a carrier-based formulation of levo-dropropizine, studying different grade of lactose, different concentration of magnesium stearate, drug load, and blending procedure. However, micronized levo-dropropizine with selected formulation didn't give satisfactory inhalation performance. Selection of levo-dropropizine as API was done due to an increase in general understanding of use and need of alternative therapies for non-productive cough that adversely affects quality of life of patients with idiopathic pulmonary fibrosis. Several treatments for cough exist on the market, but these have poor tolerability. This issue, for most antitussive on the market, is related to central nervous system side effects. Additionally, these molecules are approved for use as syrup, oral drops, and tablets forms only. Thanks to a deeper understanding of physiology and illness of the lung, pulmonary drug delivery becomes an alternative choice to treat local and systemic disease. Levo-dropropizine, a peripherally acting antitussive drug, has a well-known good tolerability and safety profile if compared with other antitussive agents that act centrally to suppress cough. In addition, curcumin has been described as having antioxidant, anti-inflammatory, and anti-carcinogenic properties, and has already been used to treat cancer, arthritis, and liver abnormalities and respiratory infections. During the present work, co-micronization with magnesium stearate and replacement of fine carrier with micronized curcumin demonstrate to improve API inhalation performance. Surprisingly, less agglomeration between particles by co-micronization technique, shape similarity of micronized curcumin with fine lactose and usage of as carrier into the formulation improve aerosolization of levo-dropropizine. Listed here are the methods used during experimental work related on micronization of levo-dropropizine and curcumin alone and in combination with magnesium stearate, using a labo jet mill to produce output powder fraction with particle size distribution below 5 microns as D50, production of lactose-based blends with micronized APIs prepared by Procept high-shear mixer equipped with 0.25 liters bowl, and API capsules filled manually with 20 mg per capsule corresponding to 3 mg dose each APIs. Manufactured blends were characterized using FT4 powder iometer, high-performance liquid chromatography to obtain blend homogeneity, laser light scattering to obtain particle size distribution, next generation impactor to obtain aerosol particle size distribution, and dose delivery. Levo-dropropizine and curcumin, both micronized and co-micronized with magnesium stearate, were prepared and fully characterized by HPLC, DSC, and XRPD to understand the feasibility and the impact of high-energy process as micronization. No differences in terms of chemical and physical properties of both APIs were observed. Same picture and particle size distribution on micronized API were also performed to compare the particles dimension and shape between the two and between different lactose monohydrate grade, normally used into DPI carrier-based formulation, as shown in the following picture. Here we can find micronized levo-dropropizine, micronized curcumin, lactose monohydrate LH300, lactose monohydrate LH230, and lactose monohydrate SV003 as reference. Levo-dropropizine micronized tends to agglomerate as shown in the same picture, while curcumin and 5-lactose monohydrate present both rectangular shapes. As well, co-micronization with magnesium stearate permits the production of a very small particle size distribution of both materials, less aggregates, and high reproducibility as shown in the table below, with the related particle size distribution of micronized and co-micronized materials. Four blends and their corresponding capsules were manufactured and fully characterized. In order to better understand the impact of each component, different compositions were studied. One with co-micronized levo-dropropizine and magnesium stearate with lactose LH230 as carrier, one with both micronized APIs using curcumin as carrier, one with co-micronized levo-dropropizine and magnesium stearate and macronized curcumin as carrier, and one with co-micronized APIs with magnesium stearate. The composition selected by previous design of experiment was added as a reference. FT4 results shown powder affected by being made to flow, probably due to the aeration and electrostatic charge of the material analyzed. This tendency is confirmed also by moderate cohesion observed by the specific energy results and flow rate index data. Higher cohesion was detected for composition 4, showing higher specific energy and flow function values, probably due to smallest particle size distribution, resulting in high electrostatic tendency. Composition 4 also exhibits less fluidized behavior, confirming higher cohesiveness as confirmed by the aerated energy and aeration ratio. Comparing APST data, co-micronization of levo-dropropizine with magnesium stearate and usage of micronized curcumin as alternative of fine carrier observed with composition 3 showed the best inhalation performance of levo-dropropizine, doubling FPD and FPF data compared to the DOE formulation. Co-micronization helps to reduce the tendency of the API, levo-dropropizine, to agglomerate, but also the micronized curcumin improved the aerosolization of levo-dropropizine itself, decreasing the retention of material inside capsules, device, and mouthpiece. Moreover, the micronized curcumin exhibits promising inhalation behavior itself. The current work permits the deeper understanding on the inhalation performance of levo-dropropizine administered as DPI, impacted by a strong agglomeration of the particles after micronization. The use of co-micronization technique with magnesium stearate in combination with micronized curcumin as fine carrier improved the aerosolization of levo-dropropizine DPI formulation, as observed with composition 3, and decreased the retention of material inside capsules, device, and mouthpiece. Moreover, the micronized curcumin itself exhibits promising inhalation behavior. Furthermore, one of the advantages of levo-dropropizine combined with curcumin could be to use it as treatment of different pathologies, such as idiopathic pulmonary fibrosis with both systemic and local effects, exploiting the pulmonary delivery, reducing side effects. Thank you so much for your attention. Here below you can find my contact and co-author's contacts if needed.